There is a particular quality to the silence that settles over land at night, when the wind has died down and the air grows still enough to feel the weight of everything above and below. The ground beneath your feet, solid and familiar, extends downward into regions that have never been touched by light, never been mapped with certainty, never been seen by human eyes. What we call Earth is mostly interior, a vast architecture of rock and metal and pressure that exists in a state of permanent darkness, moving in ways we can only infer from tremors that travel through it like whispers through stone. We stand on the thinnest imaginable shell, a surface so thin it would barely register if the planet were scaled down to the size of an apple, and beneath that shell lies almost everything we do not fully understand. If this kind of quiet reflection helps you unwind, you can subscribe to Quiet Science and continue this journey with us. There is no urgency here, only the slow work of noticing what remains just beyond the reach of direct observation. Science has given us names for the layers that compose the interior: crust, mantle, core, and those names create an impression of certainty, as if the naming itself were equivalent to knowing. But names are not the same as witness. The deeper we consider what lies below, the more we encounter boundaries defined not by sight, but by inference, not by samples, but by the behavior of waves passing through regions no drill has ever reached. The Earth keeps its structure mostly to itself, revealing it only in fragments, only in echoes, only in the gradual accumulation of evidence that suggests rather than confirms. And perhaps there is something peaceful in that, in accepting that the ground beneath us holds mysteries that will remain mysteries for as long as we are here to wonder about them. The difficulty begins with a simple fact that we rarely pause to consider. We have never seen most of the planet we live on. Not in the way we have seen the surface of Mars through rovers that crawl across its dust. Not in the way we have photographed distant galaxies through telescopes that capture light from the beginning of time. The interior of Earth remains almost entirely beyond the reach of direct observation, not because we lack the desire to look, but because the planet's own mass creates conditions that make looking impossible. The deepest hole ever drilled by human effort descended roughly 12 kilometers into the crust, a remarkable achievement that took decades of work and pushed engineering to its limits. And yet that depth represents less than 1/5 of 1% of the distance to Earth's center. It is roughly equivalent to piercing the skin of an apple with a needle and claiming to understand the apple's entire structure from that single puncture. What we call knowledge of Earth's interior is, in most cases, a careful construction built from indirect evidence, from signals that travel through rock and return changed, from fragments of deep material that occasionally rise to the surface through volcanic conduits, from theoretical models that predict how matter should behave under pressures and temperatures we cannot recreate in laboratories. This is not a failure of science. It is simply the condition of studying something from within it, of trying to map a structure while standing on its outermost edge. Consider what it means to infer rather than observe. When seismic waves from an earthquake travel through the Earth, they bend and slow and speed up depending on the materials they encounter. And by measuring these changes at stations scattered across the surface, scientists can construct a picture of what lies below, not by seeing it, but by reading the effects it has on energy passing through it. It is something like standing in a dark room and clapping your hands, then listening to how the sound returns to determine the size and shape and contents of the space around you. The method works. It produces results that align with other evidence, that allow predictions to be tested, that reveal patterns consistent across different types of measurement. But it is not the same as turning on a light. The difference matters, not because it undermines confidence in what has been learned, but because it reminds us that all models of the deep Earth are, by necessity, interpretations. They are the best explanations we have for the data we can gather, refined over decades of careful work, and they will almost certainly be revised as new data arrives, as new methods of listening and measuring are developed, as technology finds ways to ask questions that were previously unanswerable. The interior, then, exists for us primarily as a set of informed assumptions. We know, or believe we know, that beneath the crust lies the mantle, a layer of rock so thick it contains more than 80% of Earth's volume. And we know this not because anyone has traveled there or brought back samples from its depths, but because seismic waves behave in ways consistent with dense silicate minerals under immense pressure and heat. We know, or believe we know, that deeper still lies a core divided into two regions, an outer layer of liquid iron and nickel, and an inner sphere where that same material solidifies under pressures so extreme that atoms are forced into arrangements that do not exist anywhere else on the planet's surface. This knowledge comes from seismic data, from the behavior of Earth's magnetic field, from the study of iron meteorites that may represent fragments of cores from long-destroyed planetary bodies, from computer simulations that model how materials respond to conditions no laboratory can sustain. It is robust. It has withstood decades of scrutiny, and yet it remains, fundamentally, a portrait painted with echoes and absences rather than direct light. What makes this situation unusual is how confident we have become in our interpretations. The models are taught in schools as if they were settled fact, illustrated in diagrams that show clean divisions between layers, labeled with precise depths and temperatures and compositions. And in a sense, this confidence is justified. The models work. They predict the behavior of seismic waves with remarkable accuracy. They explain phenomena ranging from volcanic eruptions to the drift of continents. But confidence born from consistency is not the same as certainty born from observation. The distinction is subtle, easy to overlook, and perhaps for most purposes, unimportant. Yet there is something worth noticing in the gap between what we can measure and what we can see, between the Earth as it exists in reality and the Earth as it exists in our reconstructions of it. The planet beneath us is older than any human concept of time, composed of materials that have been cycling and transforming for billions of years, operating according to processes that unfold on timescales so slow they are invisible within a human lifetime, and most of this immense machinery functions in complete darkness, at pressures and temperatures that would annihilate any instrument we might send to observe it directly. We have learned to read its effects at the surface, to interpret the signals it sends through stone, to build theories that organize these readings into coherent narratives. But the thing itself, the actual substance and structure of the deep interior, remains something we encounter primarily through translation, through the medium of waves and models and carefully calibrated inference. Perhaps this is simply the nature of knowledge when it concerns systems too large to hold in view, processes too slow to witness unfolding, structures too remote to touch. The ocean floor was once as unknown as the deep mantle, hidden beneath miles of water that scattered light and crushed vessels before they could descend far enough to see. Now we have maps of it, incomplete but growing, assembled through years of patient sonar surveys and robotic exploration. The interior of the Earth may always resist such direct mapping, not because of technological limitations alone, but because the conditions that define it, the heat, the pressure, the sheer density of matter arranged in layers we cannot penetrate, create a kind of natural boundary around the knowable. And there is something almost fitting in this, the idea that the planet holds domains we can study without ever fully entering, regions that will remain, at least partially, beyond the reach of first-hand experience. The layer we inhabit, the one we call home, and build our cities upon, and mine for resources and study with instruments we can actually place against its surface, is almost absurdly thin when measured against the full depth of the planet. The continental crust, which forms the landmasses we walk across, averages somewhere between 30 and 50 kilometers in thickness, thicker beneath mountain ranges, where it has been compressed and folded like fabric pushed together by opposing forces, thinner in regions where the Earth has been stretched and pulled apart. This might seem substantial until you place it in context. The radius of the Earth measures roughly 6,370 kilometers from surface to center, which means the crust accounts for less than 1% of that distance, a shell so proportionally thin that if you held a globe in your hands, the crust would be thinner than the layer of varnish protecting the surface. We live on a film, essentially, a boundary condition between the solid interior and the atmosphere, and almost everything we have ever done as a species, every civilization, every structure, every mine shaft, every well, exists within this impossibly narrow band. Even here, in the region we can actually access, our understanding remains incomplete. We know the crust is composed primarily of silicate minerals, rocks rich in silicon and oxygen, with aluminum and various other elements mixed in depending on location and history. We know it formed through processes that began shortly after the planet itself coalesced from the disk of debris surrounding the young sun, as lighter materials rose toward the surface, while denser components sank inward, pulled by gravity into a rough segregation by density. We know it has been reworked countless times through the slow cycling of plate tectonics as oceanic crust forms at mid-ocean ridges and then slides back into the mantle at subduction zones, while continental crust, being lighter and more buoyant, tends to persist, accumulating over billions of years into thick, stable platforms. These are established facts, backed by observation and measurement, and the kind of repeated verification that builds confidence. And yet, there are still places on land where the geology remains only partially mapped, where the details of crustal structure are inferred from limited data, where questions about the exact sequence of ancient events remain open to interpretation and debate. The oceanic crust presents an even more complex picture, and it forms continuously along the network of mid-ocean ridges that snake through every major ocean basin, a global system of underwater mountain ranges where magma rises from the mantle and solidifies into fresh basalt, creating new seafloor at rates measured in centimeters per year. This process, the spreading of the seafloor, the creation of crust at spreading centers, and its eventual return to the mantle at subduction zones, was not confirmed until the middle of the 20th century, which is remarkably recent considering how fundamental it is to our understanding of planetary dynamics. Before that, the idea that continents could move, that the Earth's surface was not fixed and permanent, but actively recycling on timescales of hundreds of millions of years, was considered speculative at best and often dismissed outright. The evidence that changed this understanding came partly from patterns in the magnetic orientation of rocks on the ocean floor, which record reversals in Earth's magnetic field and create symmetric stripes of alternating polarity spreading out from the ridges. It came from the discovery of earthquakes clustered along specific linear zones that trace the boundaries between massive plates of lithosphere sliding past and over and beneath one another. It came from a gradual accumulation of observations that could not be explained by a static Earth and demanded a more dynamic model. What is striking about this history is how recently we arrived at a coherent picture of even the most accessible layer of the planet. The theory of plate tectonics, which now forms the foundation of geological understanding, only became widely accepted in the 1960s. Before that, the surface of Earth was thought to be essentially fixed, with mountains rising through slow vertical uplift rather than through the collision of moving plates, with ocean basins assumed to be ancient and permanent rather than young and constantly renewing. The shift to the modern view required not just new data, but a willingness to reconsider assumptions that had seemed self-evident, to accept that the ground beneath our feet was in motion, even though that motion was far too slow to perceive directly. And even now, with the broad outlines of plate tectonics established and verified through countless measurements, there are details that remain uncertain, mechanisms that are not fully explained, processes in the deeper crust that we understand in general terms, but not with complete precision. There is something instructive in this, the realization that even the layer we live on, the one we can actually sample and study and observe, has only recently been understood in its basic operation. The crust is the most accessible part of the Earth, the part where we can drill holes and collect rocks and map structures using instruments placed directly on the surface. And yet our comprehensive picture of how it works, how it forms, how it moves, how it interacts with the layers beneath it, is younger than many people currently alive. If the most accessible layer took this long to understand, if theories about it remained contested and incomplete well into the age of satellite communication and computer modeling, what does that suggest about our knowledge of the regions that lie deeper, beyond the reach of direct sampling, known only through signals that travel through them and return transformed? The question is not meant to undermine confidence in what has been learned, but rather to place that knowledge in context, to recognize that understanding the Earth is a work that has been progressing for only the briefest moment in geological time, and that what we now consider settled may look different when viewed from the perspective of future centuries. The crust, then, is both known and not fully known, both mapped and still revealing surprises, both the foundation of our existence and a reminder of how recent and provisional our understanding of even familiar things can be. It is the layer we interact with daily, the one that provides the minerals we build with and the soils we grow food in, and the bedrock that holds our structures upright. And it remains, in many ways, a frontier, a place where new discoveries continue to emerge as technology improves and as scientists find new questions to ask about old rocks. And beneath it, beyond the reach of any shovel or drill that could penetrate deep enough to cross the boundary, lies everything else. The vast interior that makes up almost the entire planet, waiting in silence for methods of observation we have not yet invented. The boundary between the crust and the layer beneath it was discovered not by digging or drilling, not by sending instruments downward into the rock, but by listening to earthquakes. In 1909, a Croatian seismologist named Andrija Mohorovičić was studying the records of an earthquake that had occurred near Zagreb, examining the traces left by seismic waves on instruments that recorded ground motion with delicate needles, scratching lines on rotating drums. He noticed something unexpected in the pattern of arrivals. The waves reached different seismograph stations at times that did not quite match what would be expected if they had all traveled through uniform material. Some waves arrived slightly earlier than they should have, as if they had taken a faster route through the Earth's interior, and the only way to explain this was to propose that somewhere beneath the surface, at a depth of perhaps 30 to 50 kilometers depending on location, there existed a boundary where the properties of rock changed abruptly. Below this boundary, seismic waves traveled faster, which suggested that the material there was denser, composed of different minerals arranged in different structures, and this transition, this invisible line separating the crust from the mantle, came to be called the Mohorovičić discontinuity, or MOHO for short, after the man who inferred its existence from the behavior of waves he could measure but never see. What Mohorovičić had discovered was a fundamental layer of Earth's architecture, one that exists everywhere beneath the surface, but remains completely inaccessible to direct observation. The MOHO marks the place where the crust ends and the mantle begins, a transition not of temperature or color or any visible quality, but of composition and density, of minerals that exist in different forms under different pressures. Above the MOHO, in the crust, the dominant rocks are relatively light, rich in silicon and aluminum, the kind of material that forms granite and basalt and the sedimentary layers that accumulate over millions of years. Below it, in the mantle, the rocks are heavier, composed primarily of olivine and pyroxene, minerals that contain more magnesium and iron, that pack together more tightly, that allow seismic waves to propagate through them at higher speeds. The boundary itself is not a surface you could touch, or a wall you could see if you somehow descended through the crust. It is simply the depth at which one type of material gives way to another, where the pressure and temperature become sufficient for different mineral assemblages to be stable, where the character of the planet changes, even though the change is defined by properties, rather than by any visible line of demarcation. This method of discovery, this reading of boundaries through the behavior of waves, represents one of the fundamental ways we have learned to see into regions we cannot access. Earthquakes generate waves that radiate outward from their source in all directions, traveling through the body of the planet and along its surface, bending and reflecting and refracting wherever they encounter changes in material properties. By placing seismographs at many locations and measuring when waves arrive and how strong they are and what their character reveals about the paths they took, scientists can construct a picture of Earth's interior much the way you might infer the shape of an object by touching it in darkness, by learning its contours through contact rather than sight. The method is indirect but powerful. It has revealed not only the MOHO, but also deeper boundaries, the transition between the upper and lower mantle, the boundary between mantle and core, the division within the core itself between liquid outer and solid inner regions. Each of these discoveries came from patterns in seismic data, from the realization that waves were behaving in ways that required specific structures to exist at specific depths, structures that could then be modeled and tested against additional observations until a consistent picture emerged. The remarkable thing about this approach is how much certainty can be built from echoes. We have never seen the moho directly, never placed an instrument against it, or collected a sample from the precise depth where crust transitions to mantle in a way that preserved the boundary intact. The deepest drilling projects have come close. Boreholes on the ocean floor have penetrated into the uppermost mantle in a few locations where the crust is thinner than average. But even these efforts represent extraordinary technical achievements that barely scratch the surface of what lies below. For the most part, our knowledge of the moho comes entirely from seismic data, from the accumulated records of thousands of earthquakes measured at thousands of stations over more than a century, analyzed and reanalyzed and refined into models that predict wave behavior with impressive accuracy. The confidence we have in the existence of this boundary is not born from seeing it, but from the consistency with which seismic waves reflect its presence, from the way multiple lines of evidence all point toward the same conclusion, from the absence of any alternative explanation that fits the data as well. There is something almost poetic in the fact that one of Earth's most fundamental boundaries was discovered by a person studying earthquakes in a small city in Croatia, working with instruments that were primitive by modern standards, analyzing data by hand in an era before computers could process thousands of measurements simultaneously. Mohorovičić was not searching for a discontinuity when he found it. He was trying to understand the pattern of seismic arrivals from a particular earthquake, and the boundary emerged as the explanation his data demanded. This is often how knowledge advances, not through sudden revelations, but through careful attention to details that do not quite fit existing models, through the willingness to propose new structures when old explanations prove inadequate. The discovery did not come with fanfare. It took years for the idea to be accepted, for other seismologists to confirm that the same boundary appeared in data from different earthquakes in different regions, for the concept of a global discontinuity separating crust from mantle to become part of the standard understanding of planetary structure. And even now, more than a century later, the exact depth and character of the moho varies from place to place in ways that are still being mapped and studied, because Earth is not uniform, because its layers have been shaped by billions of years of geological history, because every boundary contains complexities that simple models smooth over in the interest of clarity. What Mohorovičić's work established was not just the existence of a boundary, but a method, a way of using energy that travels through the Earth to reveal structures that lie beyond the reach of direct observation. Every boundary discovered since then has followed the same basic approach: reading patterns in seismic waves to infer the presence of transitions we cannot see, building models that organize these inferences into coherent pictures of planetary architecture. And perhaps what makes this method particularly striking is how it forces us to accept knowledge that comes without the comfort of visual confirmation, understanding that rests on interpretation rather than witness, certainty built from the consistent behavior of waves traveling through darkness toward instruments that record their arrival and allow us, from those recordings, to imagine the structure they passed through on their journey. Below the moho lies a region so vast it dwarfs everything above it, a layer that extends from the base of the crust down nearly 3,000 kilometers toward the center of the planet, containing more than 80% of Earth's total volume. The mantle is not a single uniform mass, but rather a gradual transition of rock that changes in density and temperature and mineral structure as depth increases, responding to pressures that rise steadily from roughly 200,000 times atmospheric pressure at the top to over 1,000,000 times that pressure at its deepest point, where it meets the outer core. This is a domain where familiar concepts of solid and liquid begin to blur, where rock that would shatter like glass if struck at the surface flows like honey over geological time, deforming slowly under its own immense weight, convecting in patterns that take millions of years to complete a single cycle. We know this layer exists. We have measured its effects through seismic waves, through volcanic eruptions that bring fragments of it to the surface, through the slow drift of continents that reveals convection currents churning beneath the crust. And yet we have never seen it directly, never sampled it in place, never observed its structure with instruments that could report back from the depths where it actually resides. What we understand about the mantle comes primarily from three sources, each providing a different kind of evidence, each adding a piece to a picture that remains incomplete. The first source is seismic data, the same method that revealed the moho, and continues to map variations in wave speed throughout the interior. These measurements show that the mantle is not homogeneous, but contains regions where waves travel faster or slower than average, indicating variations in temperature or composition or both. And these variations suggest the presence of convection, hot material rising from deep within the mantle toward the base of the crust, cooling as it spreads laterally beneath the plates, then descending again in cold downwellings that sink toward the core mantle boundary. The pattern is complex, not the simple overturning that might occur in a pot of water heated from below, but a three-dimensional flow influenced by the viscosity of rock, by the geometry of the mantle itself, by the presence of subducting slabs of oceanic crust that penetrate deep into the interior and create disturbances in the flow. Seismic tomography, the technique that produces these images, works much like a medical CT scan, building up a three-dimensional picture from thousands of individual measurements, and the results show a mantle that is dynamic and heterogeneous, far more complex than early models suggested. The second source of information comes from samples of mantle rock that occasionally make their way to the surface, brought up either as fragments caught in rising magma or as pieces of ocean floor that have been thrust onto land through tectonic collisions. These samples, called xenoliths when they arrive as inclusions in volcanic rock, or ophiolites when they represent sections of oceanic lithosphere that have been abducted onto continental margins, provide direct evidence of what mantle material looks like, what minerals compose it, what its texture and chemistry reveal about conditions at depth. The most common type of mantle rock found in these samples is peridotite, a dense greenish stone composed primarily of olivine and pyroxene, the minerals that seismic data suggest should dominate the upper mantle. Examining these rocks under microscopes, analyzing their chemical composition, studying the tiny inclusions trapped within their crystals, all of this provides constraints on temperature and pressure, and the processes that occur in regions we cannot otherwise access. But there is a limitation built into this method. The samples come only from the uppermost mantle or from specific geological settings, where unusual circumstances have brought deeper material toward the surface. They do not represent a systematic survey. They are fragments, messengers from below, offering glimpses of a larger reality that remains mostly hidden. The third source of knowledge comes from laboratory experiments and theoretical modeling, attempts to recreate mantle conditions in controlled settings, and to predict how materials should behave under extreme pressure and temperature. By squeezing samples of rock in diamond anvil cells, devices that can generate pressures equivalent to those found hundreds of kilometers below the surface, and heating them with lasers, scientists can observe how minerals transform, how their crystal structures change, how their properties evolve as conditions shift. These experiments help confirm interpretations of seismic data, showing that certain wave speed changes observed at specific depths correspond to known phase transitions where minerals reorganize into denser configurations. They help predict the viscosity of mantle rock, its ability to flow, the timescales over which convection should operate, and they help identify which materials are likely to be present at different depths, constructing a profile of the mantle that moves from direct observation of surface samples, through inference based on seismic behavior, to prediction based on what physics and chemistry say should exist under such extreme conditions. What emerges from these three lines of evidence is a picture of the mantle as a layered, slowly churning region of hot rock, gradually cooling over billions of years as heat generated during Earth's formation and sustained by radioactive decay in the interior leaks out toward the surface. The upper mantle, extending down to about 400 kilometers, appears to be relatively active, participating directly in plate tectonics, with portions of it attached to the underside of crustal plates and moving with them as rigid lithosphere. Below that lies a transition zone where minerals undergo phase changes, reorganizing their atomic structures under increasing pressure, becoming denser without changing their basic composition. Deeper still, the lower mantle extends from roughly 660 kilometers down to the core mantle boundary at 2,900 kilometers. A vast region where convection is slower, where the rock is stiffer, where the conditions are so extreme that only indirect measurements can reveal what occurs there. Each of these regions is known not through direct observation, but through the combined interpretation of seismic waves, laboratory experiments, and fragments that have reached the surface, a synthesis that creates understanding while acknowledging the limits of what can be verified. Perhaps the most striking aspect of our knowledge about the mantle is how much of it rests on consistency rather than certainty, on the agreement between different types of evidence rather than on any single definitive measurement. No one has touched mantle rock in its native environment, felt its texture at depth, observed its behavior while it flows. Instead, we have built a model from signals and samples and simulations, each piece adding confidence, each new finding either supporting or requiring adjustments to the picture we hold. And the picture that emerges is one of a vast, patient, slowly moving region that operates on timescales that make human lifespans appear as brief flickers, a layer that has been convecting for billions of years, carrying heat from the interior toward the surface, driving the motion of plates, reshaping continents, and doing all of this in complete darkness and silence, known to us only through the traces it leaves in the world we can measure. The movement of the mantle, if it can even be called movement in any sense that human experience would recognize, occurs at rates that make the growth of mountains seem sudden. Rock flows downward from cold subducting slabs at perhaps a few centimeters per year, rises from hot plumes at similarly glacial speeds, spreading laterally beneath the crust in currents that take tens of millions of years to complete a single circulation. This is convection, the same basic process that occurs when water boils in a pot or air currents form in a heated room, but stretched across scales of time and pressure that transform it into something almost unrecognizable. The mantle is solid by any definition that matters. If you could somehow reach down and touch it, it would feel as hard and unyielding as any rock you might pick up from the ground. And yet over the span of geological epochs, it deforms and flows, responding to temperature differences that drive denser, cooler material downward, while hotter, more buoyant rock rises to take its place. We have never watched this happen. We cannot. The timescales involved are so far beyond human perception that the flow is invisible not because it occurs in darkness or at depth, but because it unfolds too slowly for any observation shorter than millions of years to capture it in motion. What allows solid rock to behave like a fluid is not a change in its fundamental nature, but the patient accumulation of strain over time. At the temperatures and pressures that exist in the mantle, minerals can deform through processes that operate at the atomic scale. Atoms migrating slowly through crystal lattices, grain boundaries sliding past one another with imperceptible gradualness, tiny fractures forming and healing as stress redistributes itself through the rock. These processes are not visible in any sample you could hold, not measurable over time spans you could observe in a laboratory, but given millions of years they accumulate into motion, into flow, into the slow overturning of material that carries heat from the deep interior toward the surface. The rock never melts, never loses its solid character, and yet it moves nonetheless, obeying the same principles that govern all convection. Hot material rises because it is less dense, cool material sinks because it is heavier, and the system gradually transports heat from regions where it is abundant to regions where it is scarce, trying always to reach equilibrium even though new heat is constantly being added from radioactive decay and from the residual warmth of Earth's formation. The evidence for this convection comes not from watching it happen, but from seeing its consequences. The motion of tectonic plates at the surface, continents drifting, ocean basins opening and closing, mountain ranges rising where plates collide. All of this requires forces generated in the mantle below. The pattern of heat flow measured at the surface shows variations that suggest upwelling currents beneath some regions and downwelling currents beneath others. Seismic tomography reveals three-dimensional structures in the mantle that look like what you would expect to see in a convecting fluid. Cold slabs of subducted oceanic crust descending into the deep interior. hot plumes rising from near the core mantle boundary, regions of faster and slower wave speeds that correlate with temperature variations. Computer simulations that model how the mantle should behave, given its viscosity and the heat sources driving it, produce patterns that match these observations, showing that convection with the properties inferred from seismic data and laboratory experiments would naturally generate the kind of plate motion we observe at the surface. The agreement between these different lines of evidence, the surface motions, the seismic structure, the heat flow patterns, the computer models, builds confidence that convection is indeed occurring, even though no one has witnessed the actual flow, even though the timescales involved place it beyond the realm of direct observation. What this means is that the interior of the planet has been in motion for as long as it has existed in anything like its current form, perhaps for more than 4 billion years, cycling material slowly between the deep mantle and the regions just beneath the crust. Some pieces of oceanic crust that form at mid-ocean ridges travel across the seafloor for 100 million years before reaching a subduction zone and descending back into the mantle. Once subducted, they sink through the upper mantle over the course of tens of millions of years, perhaps penetrating all the way to the core mantle boundary, perhaps stalling somewhere in the transition zone between upper and lower mantle. Eventually, after hundreds of millions of years spent in the deep interior, they may rise again as part of a hot upwelling, their minerals transformed by pressure and temperature, their chemical signatures altered but not erased, their history written in isotopic ratios and trace element concentrations that can be read by geochemists studying volcanic rocks at the surface. The entire cycle, from formation at a ridge, to subduction, to residence in the deep mantle, to eventual return in a mantle plume, might take 500 million years or more, and during most of that time the material moves through regions we cannot see, following paths we can only infer, participating in flows that operate in complete silence and darkness. There is something humbling in trying to hold this image in mind. The idea of rock flowing through the interior on timescales so vast that entire mountain ranges rise and erode away during a single circulation. The mantle does not rush. It has no need to. The processes that drive it, the slow decay of radioactive isotopes, the gradual cooling of the planet's primordial heat, operate over billions of years, and the convection they power matches that patience. Heat moves through solid stone the way winter cold seeps through the walls of a building, not in a sudden transfer but through gradual diffusion, molecule by molecule, across distances measured in thousands of kilometers. The currents that form in response to this heat transport are imperceptible within any human lifetime, invisible across the span of recorded history, detectable only through the accumulated observations of geology, through the recognition that continents have moved and oceans have opened and closed, through the realization that these changes require forces and motions operating beneath the surface, at scales we can measure but never directly witness. Perhaps it is fitting that the largest and most fundamental motion within the planet, the convection that drives everything from plate tectonics to volcanic activity to the magnetic field, occurs at a pace that places it almost entirely beyond human observation, knowable through its effects, but never through direct sight. The mantle has been flowing since before life existed on Earth, and it will continue flowing long after any civilization has ended, patient and indifferent, carrying heat toward the surface in a process that has no urgency, no endpoint, only the slow working out of physical laws across timescales that make human concerns appear momentary. At certain depths within the mantle, something changes in the rock, not its chemical composition, not the elements that make it up, but the way those elements arrange themselves into crystalline structures. These transitions occur at specific pressures, where one mineral configuration becomes unstable and reorganizes into a denser form, the atoms shifting their positions to pack more tightly together, occupying less space per unit of mass. The first major transition happens at around 410 kilometers below the surface, where the mineral olivine, which dominates the upper mantle, transforms into a denser phase called wadsleyite. The change is sudden in geological terms. It occurs over a depth range of just a few kilometers, but it is invisible in every sense except the one that matters for detection. Seismic waves passing through this depth speed up abruptly, their velocity increasing as they enter rock that has reorganized into a more compact structure. And it is this change in wave speed that reveals the boundary's existence. There is no visible line marking the transition, no shift in color or texture, or anything that could be seen if you somehow descended through it. The rock above and the rock below are made of the same elements in the same proportions. Only the arrangement has changed, responding to pressure that has reached a threshold where the old configuration can no longer be maintained. This region, extending from roughly 400 to 660 kilometers in depth, is known as the transition zone, not because it is fundamentally different from the mantle above and below it, but because it contains several of these phase transitions, places where minerals reorganize into progressively denser structures as pressure continues to increase. Deeper in the transition zone, around 520 kilometers down, Wadsleyite itself transforms into yet another denser phase called ringwoodite, again without any change in chemical composition, again marked only by an increase in seismic wave speed. And at the base of the transition zone, near 660 kilometers, ringwoodite breaks apart into two different minerals, bridgmanite and ferropericlase, in what represents the most significant phase transition in Earth's mantle, a transformation that marks the boundary between the transition zone and the lower mantle and creates one of the sharpest changes in seismic properties anywhere in the planet's interior. These transitions are boundaries defined entirely by behavior rather than substance, divisions that exist because pressure forces matter into different configurations, and they represent some of the most precisely identified features in the deep Earth despite being invisible and inaccessible to any form of direct observation. What makes these phase transitions particularly interesting is that they can be recreated in laboratories, allowing scientists to verify that the seismic discontinuities observed at specific depths correspond to mineral transformations that occur at those pressures. By placing samples of mantle minerals in diamond anvil cells, devices that squeeze material between two precisely cut diamonds, generating pressures equivalent to hundreds of kilometers of depth, and heating them to mantle temperatures, researchers can watch as the minerals transform, as their crystal structures reorganize, as their densities increase in ways that match the seismic data. The experiments confirm what the seismic observations suggest, that the discontinuities at 410 kilometers and 660 kilometers are not compositional boundaries, but phase boundaries, places where the same material exists in different forms above and below. This kind of verification, where laboratory results and seismic data point to the same conclusion, builds confidence in interpretations that cannot be tested through direct sampling. It shows that understanding can emerge from combining different approaches, from using experiments to constrain what seismic waves are detecting, from building a picture that remains consistent across multiple lines of evidence, even though the actual region being studied lies beyond reach. The existence of these phase transitions has implications for how the mantle behaves, for how convection operates, for how material moves between the upper and lower mantle. Some models suggest that the 660-kilometer discontinuity acts as a partial barrier to flow, that descending slabs of cold oceanic crust may stall at this depth, at least temporarily, because crossing the phase transition requires energy and time and conditions that are not always present. Other models suggest that material can pass through relatively easily, that the transition zone is not a significant impediment to whole mantle convection. Seismic imaging shows some slabs penetrating deep into the lower mantle, while others appear to flatten out near the 660-kilometer boundary, suggesting that the dynamics are complex and perhaps variable, depending on temperature and composition and the geometry of the sinking material. The uncertainty here is not about whether the phase transitions exist, that is well established, but about exactly how they influence the larger scale behavior of the mantle, how they interact with convection currents that operate over hundreds of millions of years, how they shape the distribution of heat and material throughout the interior. These are questions that require both seismic observations and computer modeling, both laboratory experiments and theoretical understanding, and the answers remain topics of active research precisely because the processes being studied occur at depths and over timescales that resist direct measurement. What strikes me about these boundaries is how they highlight the strangeness of the deep Earth, the way it operates according to principles that make sense in theory, but feel counterintuitive when you try to imagine them. A boundary that is not a boundary in any conventional sense, where identical materials exist in different forms on either side of an invisible line, defined only by the pressure that has crossed a threshold where one atomic arrangement becomes less stable than another. You could not see the transition if you passed through it, could not feel it, could not detect it, through any means, except by measuring how fast seismic waves travel and noticing that their speed has increased. And yet this invisible boundary, this reorganization of atoms occurring across a few kilometers of depth 600 kilometers beneath your feet, has been mapped globally, its exact depth traced across different regions, its properties studied through hundreds of seismic studies and laboratory experiments, until what began as an inference, a guess about why waves behave strangely at certain depths, became one of the best understood features of the mantle's structure. Perhaps what these phase transitions reveal most clearly is that the categories we use to understand the world, solid versus liquid, one layer versus another, this material versus that material, are sometimes inadequate for describing what actually exists at depth. The transition zone is not a separate layer in the way the crust is separate from the mantle. It is the same mantle, the same ongoing convection, the same slow flow of rock responding to heat and pressure. The transitions are simply places where pressure has reached values that favor different atomic configurations, and the boundaries they create are real enough to show up clearly in seismic data, but invisible enough that they could never be observed directly, knowable only through the way they modify waves that pass through them on their journey from earthquakes to seismographs scattered across the surface. Below the transition zone lies the lower mantle, a region that extends from 660 kilometers down to the boundary, with the core at 2,900 kilometers, making it the single largest subdivision of the planet by volume. Nearly half of Earth's entire mass resides in this layer, compressed under pressures that begin at around 24 million times atmospheric pressure and rise to over 130 million times that pressure at its base. To say these conditions are extreme understates the matter. The rock here exists under forces that would turn any familiar material into something unrecognizable, where atoms are squeezed so tightly together that their electron clouds overlap, where the normal rules that govern how matter behaves at the surface must be extended and modified to account for densities and pressures that have no equivalent in human experience. We understand the lower mantle primarily through inference, through seismic wave speeds that suggest certain minerals must be present, through laboratory experiments that attempt to recreate these conditions in diamond anvil cells, through computer simulations that model how matter should behave when subjected to such extremes. But the gap between what we can observe and what actually exists at depth grows wider here. The uncertainties multiply, and what we call knowledge begins to shade more obviously into educated interpretation. The dominant minerals in the lower mantle are thought to be bridgmanite and ferropericlase, phases that form when the transition zone minerals break apart under the pressures found below 660 kilometers. Bridgmanite, which makes up perhaps 70 to 80% of the lower mantle by volume, is a dense silicate with a perovskite crystal structure, a particular arrangement of silicon, oxygen, and magnesium atoms that allows them to pack together more efficiently than the structures stable at lower pressures. Ferropericlase, making up most of the remaining volume, consists primarily of magnesium and iron oxide arranged in a simple cubic structure that is even denser than bridgmanite. These minerals have been studied extensively in laboratories, synthesized under high pressure and temperature, their properties measured and catalogued with considerable precision. And yet, there is something unsettling about claiming to know what dominates the lower mantle when no sample of lower mantle rock has ever been recovered, when the minerals can only be studied under conditions that approximate but do not fully replicate the environment where they actually exist, when the very act of bringing them to the surface would cause them to transform back into lower pressure phases, erasing the structures that define them at depth. What seismic data reveals about the lower mantle is that it is more uniform than the regions above it, less marked by sharp variations in wave speed, suggesting a layer where temperature and composition change more gradually with depth. This uniformity might indicate that convection in the lower mantle is slower and less vigorous than in the upper mantle, perhaps because the rock is stiffer here, its viscosity increased by the immense pressure, its ability to deform reduced, even though it remains technically solid. Some seismic images show large regions near the base of the lower mantle where wave speeds are notably slower than average, structures known as large, low-shear velocity provinces, which may represent piles of dense material that have accumulated over billions of years, perhaps the remnants of ancient oceanic crust that descended through subduction zones and settled at the bottom of the mantle like sediment falling to the floor of a deep ocean. These structures, if they exist as the seismic data suggests, would be continent-sized masses of rock, denser and perhaps chemically distinct from the surrounding mantle, and their presence would have implications for how heat escapes from the core, for how mantle plumes form and rise toward the surface, for the long-term evolution of the planet's interior. But all of this remains interpretive. The structures are detected through variations in seismic wave speed, not observed directly, and multiple explanations for those variations remain plausible. The temperature in the lower mantle increases gradually with depth, driven by heat conducted upward from the core and by the continued decay of radioactive isotopes distributed throughout the mantle itself. Near the top of the lower mantle, temperatures are estimated to be around 1600 to 1800 degrees Celsius, hot enough to make the rock glow if it could somehow be observed. At the base, near the core mantle boundary, temperatures are thought to reach 3000 to 4000 degrees Celsius, approaching the temperature of the sun's surface, though these estimates come with considerable uncertainty because measuring temperature at such depths is impossible with current technology. The numbers are derived from models that account for heat sources within the Earth, for the rate at which heat flows through rock, for the properties of minerals under extreme pressure, and while the models are sophisticated and based on sound physics, they remain models, constructions that represent our best understanding, given the constraints available, not measurements taken from the region they describe. The actual temperature at any given depth in the lower mantle is something we infer rather than know, something we estimate within a range of possible values rather than determine with precision. What makes the lower mantle particularly difficult to study is that its properties lie at the edge of what laboratory experiments can reliably reproduce. The pressures found at the base of the lower mantle approach 140 gigapascals, pressures that require extraordinary effort to generate even for tiny samples held between diamonds. Pressures where the behavior of materials becomes increasingly uncertain, where theoretical predictions begin to diverge from one another, where different models of atomic interactions produce different results. The temperatures, combined with these pressures, create conditions that cannot be sustained for long periods in any experimental apparatus, which means that understanding how the lower mantle deforms, how quickly it can flow, how it responds to forces acting on it over millions of years, all of this must be extrapolated from experiments conducted at lower pressures and temperatures, extended through theoretical frameworks that predict how matter should behave under conditions we cannot fully recreate. The gap between what can be measured in a laboratory and what exists at depth is bridged by theory, by models that have proven reliable in other contexts, by the assumption that physical laws continue to apply even in environments far beyond those where they were first tested. And perhaps that assumption is justified. The evidence suggests it is. But it is still an assumption, a necessary leap from the knowable to the inferred, and the lower mantle represents a region where that leap grows longer and more uncertain. There is a certain poetry in the fact that the largest region of the planet, the layer that contains more mass than all the rest combined, is also one of the least directly knowable, understood primarily through echoes and extrapolations and models that extend our knowledge into realms we cannot visit. The lower mantle has been in place for billions of years, slowly convecting, slowly transporting heat from the core toward the surface, slowly participating in the cycling of material that drives plate tectonics and shapes the surface world. And it has done all of this without ever being seen, without ever revealing itself except through the subtle changes it imparts to seismic waves passing through it, through the volcanic rocks that may carry traces of its composition, through the theoretical, predictions that describe what should exist under such profound compression. At 2,900 kilometers below the surface, something fundamental changes in the planet's structure. The transition is abrupt, marked by a discontinuity as sharp as any boundary detected through seismic waves, sharper in fact than most. Here the mantle, for all its heat and pressure and slow convecting motion, gives way to the core, and the change is not subtle. Seismic waves that have traveled through thousands of kilometers of solid rock suddenly encounter a region where their behavior transforms completely. Waves that compress and expand the material they pass through, called P waves or primary waves, continue onward into the core, though they slow dramatically, their velocity dropping by nearly half. But waves that propagate through shearing motion, called S waves or secondary waves, simply stop. They do not pass through the outer core at all, creating a shadow zone on the opposite side of the planet from any earthquake large enough to generate them, a region where seismographs detect P waves, but no S waves arrive. This observation, first noticed in the early 20th century by seismologists studying the distribution of earthquake signals, led to one of the most significant inferences about Earth's interior, that the outer core must be liquid, because S waves cannot propagate through fluids, cannot transmit the shearing motion that defines them through a medium that has no rigidity, no resistance to being deformed by sliding forces. The discovery that Earth contains a liquid layer deep within its interior was not obvious and not immediately accepted. The idea contradicted earlier assumptions that the entire planet was solid, compressed by its own weight into rock all the way to the center. But the seismic evidence was unmistakable. The shadow zone where S waves did not arrive, the dramatic slowing of P waves passing through the region below 2,900 kilometers, the patterns of wave arrivals that could only be explained if something fundamentally different existed at depth, all of this pointed toward the presence of a liquid outer core. The inference has been tested and refined over more than a century of seismic observations, and the conclusion has grown stronger with each new earthquake recorded, each new seismograph installed, each improvement in the methods used to analyze wave propagation. And yet, the outer core itself has never been observed directly, never been sampled, never been touched by any instrument that could report on its actual condition. What we know about it comes entirely from how it affects seismic waves, from theoretical models of how liquid metal should behave under extreme pressure and temperature, from the existence of Earth's magnetic field, which requires a conducting fluid in motion to generate and sustain it. The outer core is thought to be composed primarily of iron, mixed with perhaps 10 to 15% lighter elements, likely sulfur, oxygen, silicon, or some combination of these, that reduce its density enough to match what seismic wave speeds suggest. Pure iron at the pressures found in the core would be denser than the seismic data indicates, which means something else must be present, something that makes the liquid slightly less dense than pure iron would be. And identifying exactly what those light elements are remains a topic of active research. The candidates are elements that could plausibly exist in the core based on their behavior during the planet's formation, when heavier materials sank toward the center and lighter materials rose toward the surface in a process called differentiation. But confirming which elements are actually there, in what proportions, at what depths, this requires combining seismic observations with laboratory experiments that measure the properties of iron alloys under core conditions, with cosmochemical models that predict what materials should have been available when Earth formed, with theories about how elements partition themselves between metal and silicate at high temperatures. The result is an educated estimate, a model that fits the available evidence, not a definitive measurement. The temperature in the outer core is estimated to range from around 4,000 degrees Celsius at the top, near the core mantle boundary, to perhaps 5,000 or more degrees Celsius at its base, where it meets the inner core. These temperatures, combined with pressures that range from 135 to 330 gigapascals, create an environment where iron exists as a liquid, not a viscous magma-like substance, but a fluid with viscosity similar to water, flowing and circulating in response to heat gradients, and the forces generated by Earth's rotation. This liquid metal is in constant motion, driven by convection currents that arise because the core is cooling slowly over geological time, losing heat to the mantle above it, and as it cools, lighter elements may separate from the heavier iron, rising toward the top of the outer core while denser material sinks, creating flows that interact with the planet's rotation to generate complex three-dimensional current patterns. These currents, flowing through electrically conducting liquid metal, create and sustain Earth's magnetic field through a process known as the geodynamo, a self-sustaining mechanism where motion generates magnetic fields, and magnetic fields in turn influence the motion, creating a feedback loop that has operated for billions of years. The magnetic field produced by this process extends far beyond Earth's surface, creating a magnetosphere that deflects charged particles from the solar wind and protects the atmosphere from being gradually stripped away. The field is not static, it varies in strength, it wanders in direction, it has reversed its polarity hundreds of times throughout geological history, flipping north and south magnetic poles in events that leave records in rocks that formed during those transitions. These reversals, recorded in the magnetic orientations of minerals in oceanic crust and in sedimentary layers on land, provide evidence that the geodynamo is dynamic, that the currents in the outer core reorganize themselves in ways that are not fully understood, that the magnetic field we measure at the surface is the product of processes occurring in a liquid metal ocean we have never seen, driven by forces we can model but not observe directly. The fact that Earth has a magnetic field at all, that it has persisted for most of the planet's history, that it continues to exist and fluctuate in ways we can measure, all of this confirms that the outer core must be liquid, must be in motion, must be conducting electricity as it flows. But the details of how the dynamo operates, how the currents organize themselves, why the field reverses at irregular intervals, these remain partly mysterious, constrained by theory and simulation, but not by direct observation. What strikes me as remarkable is that one of Earth's most important features, the magnetic field that shields the surface from solar radiation, that allows compasses to function, that creates auroras when charged particles interact with the upper atmosphere, originates in a region that lies permanently beyond reach, in a sea of molten metal flowing through darkness, under conditions no human technology could survive, generating a field through processes that can be modeled but never directly witnessed. The outer core has been liquid since shortly after Earth formed, circulating for more than 4 billion years, quietly maintaining the magnetic field that makes the surface world habitable. And it will continue this work for billions of years more, patient and invisible, known to us only through the effects it produces in the world we can measure. At the very center of the planet, surrounded by the liquid outer core, lies a sphere of solid metal, roughly 1,200 kilometers in radius, about the size of the Moon, if you could somehow extract it and place it in space. This is the inner core, and its existence was inferred only in 1936, when a seismologist named Inge Lehmann, studying earthquake records from stations in Denmark and other locations, noticed faint P waves arriving at times and locations that should have been in the shadow zone if the core were entirely liquid. The only way to explain these unexpected arrivals was to propose that deep within the liquid core, there existed a solid region that could reflect and refract P waves in ways that allowed them to reach places they otherwise could not, creating signals where there should have been silence. Lehmann's interpretation was initially met with skepticism. The idea of a solid sphere at the center of a liquid layer seemed counterintuitive, and the evidence was subtle, requiring careful analysis of weak signals that were difficult to distinguish from noise. But as more earthquakes were recorded and more seismic data accumulated, the pattern became clearer. The solid inner core emerged as the only explanation that fit the observations, and what had been a tentative hypothesis became an accepted feature of Earth's structure. The inner core is solid, not because it is colder than the liquid surrounding it. In fact, the temperature at the center of Earth is estimated to be slightly higher than at the boundary between inner and outer core, perhaps 5,000 to 6,000 degrees Celsius, though these numbers carry significant uncertainty. It is solid because pressure at that depth, reaching 360 gigapascals at the very center, forces iron atoms into crystalline arrangements that remain stable despite the heat, creating a material that has crossed a threshold where the solid phase becomes energetically favorable, even at temperatures that would melt iron under lower pressure. This is the same principle that allows ice to exist at the bottom of deep oceans, despite temperatures above freezing. Pressure shifts the boundaries between phases, making solid structures stable under conditions where they would not otherwise persist. The inner core represents an extreme example of this phenomenon, a place where metal that should be liquid if it existed at the surface remains solid, because the weight of the entire planet pressing down on it creates conditions that favor crystalline order over the disorder of a liquid state. What we know about the inner core comes almost entirely from seismic waves, and the knowledge is more limited here than for any other region of the planet. The waves that reach the inner core have already traveled through thousands of kilometers of mantle and outer core, and by the time they arrive at the boundary between liquid and solid, they have been refracted and reflected and attenuated to the point where detecting them at the surface requires sensitive instruments and careful analysis. The signals that return from the inner core are faint, often mixed with other waves that have taken different paths. And extracting information about the inner core's properties from these signals requires sophisticated processing techniques and assumptions about how waves should behave in iron under extreme conditions. The result is a picture that is less detailed, less certain, more dependent on theoretical models than for any other layer. We can say that the inner core exists, that it is solid, that it is composed primarily of iron and nickel, but beyond these basic facts, much remains uncertain or debated. One of the ongoing questions concerns the structure of the inner core itself, whether it is uniform or contains internal variations, whether it has layers or regions with different properties, whether the iron that composes it is organized in a single crystalline arrangement or in multiple orientations. Some seismic studies suggest that the inner core is anisotropic, meaning that seismic waves travel faster in certain directions than in others, which would imply that the iron crystals are aligned preferentially rather than randomly oriented. Other studies suggest more complex patterns, perhaps with an innermost region where the anisotropy differs from the outer part of the inner core, or regions where wave speeds vary in ways that suggest compositional differences or structural variations. The evidence is fragmentary, and different studies sometimes reach different conclusions, which is not surprising given how difficult it is to extract clear signals from such a remote region. The uncertainty is built into the problem. There are simply not many earthquakes large enough and well-positioned enough to send clear signals through the inner core, and the paths available for seismic waves to take are limited by geometry and by the way waves refract as they pass through layers with different properties. Another question that remains unresolved is whether the inner core rotates at a different rate than the rest of the planet, a possibility that was suggested by some seismic studies in the 1990s and has been debated ever since. If the inner core does rotate independently, faster or slower than the mantle and crust, it would have implications for understanding the dynamics of the core, for how the magnetic field is generated, for how heat and angular momentum are distributed within the deep interior. But measuring such rotation requires detecting extremely subtle changes in seismic wave travel times over decades, and different analyses of the data have produced conflicting results, with some suggesting differential rotation and others finding no convincing evidence for it. The debate continues, constrained by the limited quality of data available, and by the challenge of distinguishing real changes in the inner core from variations in the paths seismic waves take, or from changes in the instruments and analysis methods used over time. What the inner core represents, perhaps more than any other region, is the limit of our ability to interrogate the planet from the surface. It is the deepest structure, the most remote, the hardest to study, and the uncertainties surrounding it are correspondingly larger. We know it exists because seismic waves behave in ways that require its presence. We know it is solid because the types of waves that reach it and return from it are consistent with reflection and transmission through a solid medium. We know it is primarily iron because that is what differentiation would predict and what the density inferred from seismic data suggests. But the details, the exact temperature, the precise composition, the crystal structure, the possibility of internal layering, the question of rotation, these remain open, subject to ongoing research, areas where different models make different predictions and where the seismic data is not yet sufficient to resolve the differences with certainty. And perhaps this is simply the nature of studying something so far removed from direct experience, so deep within a planet, that it can only be known through the faintest echoes returning from the darkness at its center. The method by which we have learned what little we know about Earth's interior, seismic tomography, works by collecting signals from thousands of earthquakes recorded at thousands of stations scattered across the surface, and using the patterns in those signals to construct three-dimensional maps of wave speed variations throughout the planet. It is something like trying to understand the structure of a room by standing in darkness and listening to how sounds reflect and refract off walls and furniture and other objects you cannot see, building up a mental picture from echoes alone. Each earthquake generates waves that radiate outward in all directions, traveling through regions with different properties, bending and slowing and speeding up depending on what they encounter. And by measuring when these waves arrive at different locations and comparing the observed travel times to what would be expected if the Earth were perfectly uniform, seismologists can infer where variations in density or temperature or composition must exist to account for the differences. The maps that result from this process are not photographs, not direct images in any conventional sense, but rather statistical reconstructions, visualizations of regions where waves consistently travel faster or slower than average, interpreted as indicators of cooler or hotter or denser or less dense material, assembled from countless individual measurements into coherent patterns that suggest structure. What makes this method powerful is its ability to reveal large-scale features that would otherwise remain completely hidden. Seismic tomography has shown cold slabs of subducted oceanic crust descending through the mantle, visible as regions of faster-than-average wave speeds that trace the paths of ancient seafloor as it sinks toward the deep interior. It has revealed hot upwellings rising from the core mantle boundary, manifested as slower-than-average wave speeds that correlate with the locations of volcanic hotspots at the surface. It has mapped variations in the thickness of the lithosphere, differences in the depth of the transition zone, heterogeneities in the lower mantle that suggest the presence of ancient compositional anomalies or regions where convection patterns differ from the global average. These are genuine discoveries, features of Earth's interior that were unknown before seismic tomography made them visible, and they have transformed understanding of how the planet works, how heat moves through it, how material circulates between surface and depth. But the images come with limitations that are sometimes easy to overlook when viewing the smooth, colorful maps that appear in textbooks and presentations. Images that can create an impression of certainty that exceeds what the data actually supports. The resolution of seismic tomography, the smallest feature it can detect, is limited by the wavelengths of the seismic waves being used and by the spacing between earthquakes and seismograph stations. Features smaller than a few hundred kilometers across are generally not resolvable in the deep mantle, and in many regions the resolution is coarser than that, determined by whether enough earthquakes have occurred in the right locations and whether enough seismographs were operating at the right times to capture the necessary signals. This means that the maps show large structures but miss smaller variations, much the way a low-resolution image shows the general shape of an object, but loses fine details. The tomographic models are averages, smoothed representations that capture the dominant patterns in wave speed variations but cannot reveal sharp boundaries or small-scale heterogeneities or any feature whose size falls below the threshold of detectability. And because the coverage is uneven, more earthquakes and more seismographs in some regions than others, the resolution varies geographically, with some parts of the mantle imaged much better than others, and with large regions beneath ocean basins or remote continental areas where data is sparse and interpretations are correspondingly less certain. There is also the matter of interpretation. A region where seismic waves travel slower than average could indicate hot rock, which would lower wave speeds, or it could indicate rock with a different composition, or it could indicate the presence of partial melt, or it could reflect some combination of these factors. Distinguishing between these possibilities requires additional information. Constraints from mineral physics experiments that predict how wave speeds should vary with temperature and composition. Models of mantle convection that suggest where hot and cold regions should exist. Comparisons with other types of data such as gravity measurements or heat flow patterns that provide independent evidence about conditions at depth. In many cases, multiple interpretations remain plausible, and the choice between them depends on assumptions about which factors are most likely to be important, which creates space for disagreement and debate, even when the seismic data itself is well established. The maps produced by different research groups using different techniques and different data sets often agree on the large features, the major cold downwellings, the broad hot upwellings, but differ in details, in how they render intermediate-sized structures, in what they suggest about regions where data is limited. This is not a failure of the method, but rather an acknowledgement of its inherent uncertainty. The recognition that constructing images from echoes requires choices about how to process the data, what assumptions to make about the Earth's structure, how to balance competing demands for resolution and reliability. What seismic tomography reveals, then, is a planet that is heterogeneous at almost every scale we can measure, with variations in temperature and composition and structure distributed throughout the mantle and core in patterns that reflect billions of years of convection and differentiation and stirring. But it also reveals the limits of knowledge built from indirect observation, the way certainty decreases as we move from the general to the specific, from large features to small ones, from well-sampled regions to areas where data is sparse. The maps are real, the features they show are real, the structures they indicate genuinely exist in some form, but the precise details, the exact temperatures, the specific compositions, the sharp boundaries between different materials, remain partly unresolved, knowable in outline but uncertain in specifics, constrained by what seismic waves can tell us, but not fully determined by that information alone. It is rather like looking at a landscape through fog, where you can see the shapes of hills and valleys and distinguish light from shadow, but where the clarity decreases with distance and the fine textures disappear into the haze. We have learned an enormous amount about Earth's interior through seismic tomography, have built maps that would have seemed impossible a century ago, have traced the motion of material through the mantle in ways that confirm theories about convection and plate tectonics. And yet the images remain, fundamentally, interpretations rather than photographs, constructions built from wave speeds rather than direct light, the best representations we can create from the limited information available, but not the same as seeing the structures themselves. The deepest hole ever drilled into the Earth's crust was completed in Russia in 1989 after more than 2 decades of continuous effort. The Kola Superdeep borehole descended 12,262 meters, just over 12 kilometers, into the Baltic Shield, one of the oldest and most stable parts of the continental crust, where conditions were thought to be relatively favorable for deep drilling, and where the geology offered opportunities to sample ancient rocks that might reveal something about the early history of the crust's formation. The project employed the most advanced drilling technology available at the time, rotating drill bits that could withstand extreme temperatures and pressures, systems for circulating drilling fluid that kept the hole stable and removed rock fragments as they were cut, methods for casing the borehole to prevent collapse in the sections already completed. And despite all of this effort, despite the technical sophistication and the years of work and the resources devoted to pushing the drill deeper than it had ever gone before, the hole penetrated less than 0.2% of the distance to Earth's center, reaching a depth that barely registered when measured against the full radius of the planet. It was, in effect, a scratch on the surface, a needle mark, a probe that confirmed just how inaccessible the interior truly is. The challenges that emerged during the drilling were instructive in themselves. As depth increased, temperatures rose faster than predicted. By the time the drill reached 12 kilometers, the temperature at the bottom of the hole had climbed to about 180 degrees Celsius, far hotter than the models had suggested, and this heat created problems for the drill bits and for the instruments being lowered into the hole to take measurements. The rock also became softer and more plastic than expected, less brittle, more prone to deforming under pressure in ways that made the hole unstable and difficult to keep open. The drilling fluid, essential for carrying rock fragments to the surface and for cooling the drill bit, began to behave unpredictably at high temperatures, losing viscosity and effectiveness. And even with all the precautions and engineering solutions implemented, the hole eventually became too difficult to maintain, the conditions too extreme for the technology available, and the project was abandoned not because it had reached its goal, but because pushing deeper would have required solving problems that exceeded what was technically feasible at the time. The project had set out to drill to 15 kilometers, perhaps deeper, but stopped at 12, not by choice, but by necessity, constrained by the same pressures and temperatures that define the deep earth and that make it fundamentally inaccessible to direct sampling. Other deep drilling projects have encountered similar limits. The German continental deep drilling program reached 9 kilometers before it was halted by high temperatures and technical difficulties. Ocean drilling projects, which can access the oceanic crust where it is thinner than continental crust, have managed to penetrate into the uppermost mantle in a few locations, drilling through 6 or 7 kilometers of crust and recovering samples of peridotite, actual mantle rock brought to the surface from the region just below the moho. These are remarkable achievements, representing the only places where humans have directly sampled material from beneath the crust. But even these efforts barely cross the boundary between crust and mantle, reaching depths that are trivial compared to the scale of the mantle itself. The samples obtained are from the shallowest part of the uppermost mantle, from regions where temperatures and pressures are still relatively moderate, where the rock has been affected by its proximity to the surface, where the conditions differ significantly from those that prevail deeper down. They are valuable, offering direct evidence of mantle composition that can be compared to what seismic data suggests, but they are not representative of the mantle as a whole, not samples from the transition zone, or the lower mantle, or the core mantle boundary, not material that has experienced the full range of conditions that exist at depth. What these drilling efforts reveal is that direct access to Earth's interior is not simply a matter of developing better technology, or drilling longer, or applying more resources. The problem is more fundamental. As depth increases, so do temperature and pressure, and both create conditions that are hostile to any instrument or drill bit or casing we might send down. Rock becomes plastic and unstable. Metal softens and deforms. Drill bits wear out quickly and must be replaced, requiring the entire drill string to be pulled back to the surface and then lowered again, a process that takes days and becomes more difficult the deeper the hole. Drilling fluid must be pumped continuously to keep the hole open and to remove cuttings. But at high temperatures, the fluid's properties change in ways that reduce its effectiveness. And beyond a certain depth, perhaps 15 or 20 kilometers, depending on location and geology, the conditions become so extreme that maintaining an open hole would require materials and methods that do not currently exist and may not be possible to develop with any foreseeable technology. The interior of the Earth is protected by its own mass, by the weight of overlying rock that creates an environment where the tools we use at the surface simply cannot function. This means that our knowledge of the deep interior will almost certainly remain indirect for as long as we exist as a species. We will continue to improve seismic tomography, to develop new ways of listening to earthquakes and processing the signals they generate, to refine our models and increase resolution and map the mantle with ever greater detail. We will continue to study the fragments of deep material that reach the surface through volcanic processes, to analyze their chemistry and mineralogy, to learn what we can from these messengers from below. We will continue to conduct laboratory experiments that recreate deep Earth conditions in miniature, squeezing samples between diamonds and heating them with lasers, measuring how they behave and using those measurements to constrain interpretations of seismic data. And all of this will improve understanding, will fill in gaps in our knowledge, will allow us to speak with greater confidence about what exists at depth. But it will not change the fundamental fact that the interior remains beyond the reach of direct observation, that we cannot go there, cannot see it, cannot place instruments in the deep mantle, or the outer core, or the inner core, and have them report back on conditions in those regions. The planet is knowable through inference and through the traces it leaves in measurements we can make at the surface, but it is not knowable through witness, not accessible to the kind of direct experience that would allow us to say with complete certainty what exists in the darkness below. Perhaps there is something fitting in this, the idea that the Earth holds regions we can study but never fully enter, places that will remain partly mysterious, not because we lack curiosity or ingenuity, but because their nature makes them fundamentally remote, separated from us, not just by distance, but by conditions that prevent crossing the distance, by pressures and temperatures that defend the interior against intrusion. The theory that explains how Earth's surface moves, the framework of plate tectonics that describes continents drifting, ocean basins opening and closing, mountains rising where plates collide, was not established until the 1960s. Before that, the dominant view held that continents were fixed in place, that the surface of the planet was essentially static except for slow vertical movements, that ocean basins were ancient permanent features rather than young structures that form and disappear over hundreds of millions of years. The idea that continents could move had been proposed earlier, most notably by Alfred Wegener in 1912, who pointed to the matching coastlines of Africa and South America to similar fossils found on continents now separated by thousands of kilometers of ocean, to evidence of ancient glaciation in regions that are now tropical. But these observations were dismissed by most geologists of the time, partly because Wegener could not explain what force would be powerful enough to push continents through solid oceanic crust, partly because the idea simply seemed implausible, too radical a departure from established understanding. It was only when new evidence emerged, particularly the magnetic patterns on the ocean floor that revealed seafloor spreading and the distribution of earthquakes that traced the boundaries between moving plates, that the old model collapsed and was replaced by something fundamentally different, a dynamic Earth where the surface is not fixed, but constantly in motion, driven by convection in the mantle below. What strikes me about this history is how recent it is. The comprehensive understanding of how the planet works, the recognition that Earth's surface is divided into rigid plates that move relative to one another, that new crust forms at mid-ocean ridges and old crust returns to the mantle at subduction zones, that continents drift not through ocean crust, but as passengers on larger plates that include both continental and oceanic lithosphere. All of this was established within living memory. There are people alive today who were taught in school that continents do not move, who learned geology before plate tectonics transformed the field, who witnessed the shift from one paradigm to another as new data made the old explanations untenable. The transformation happened quickly once the key evidence became available, within a decade or so, as researchers recognized that plate tectonics could explain phenomena that had previously seemed unrelated. The distribution of earthquakes and volcanoes, the ages of rocks on the ocean floor, the patterns of mountain building, the occurrence of certain types of ore deposits. But the speed of the shift should not obscure the fact that for most of human history, and for most of the history of geology as a scientific discipline, the basic mechanism that shapes Earth's surface was unknown, not understood, not even seriously considered as a possibility by the majority of scientists studying the planet. This is not a story about ignorance or failure. The geologists who worked before plate tectonics developed sophisticated theories to explain the observations they could make, theories that were internally consistent and that organized the available evidence into coherent frameworks. They mapped rock formations, classified minerals, studied the processes of erosion and sedimentation and volcanic activity, built up a detailed picture of Earth's surface geology without understanding the larger mechanism that drives it. They were not lacking in intelligence or curiosity or rigor. They simply did not have access to the key pieces of evidence that would eventually reveal the dynamic nature of the crust, evidence that came from technologies that did not exist until the mid-20th century, from oceanographic surveys that mapped the seafloor, from seismograph networks that traced the distribution of earthquakes with precision, from paleomagnetic studies that measured the orientation of ancient magnetic fields recorded in rocks. Once this evidence became available, the field transformed, and plate tectonics emerged as the unifying theory that tied together disparate observations and provided a framework for understanding how the planet works. But the transformation required specific kinds of data that were not accessible until relatively recently. And without that data, the earlier theories, however inadequate they now appear, were the best explanations available given the constraints of what could be observed and measured. The lesson here, if there is one, concerns the provisional nature of understanding when it deals with systems too large to observe in their entirety, processes too slow to witness unfolding, structures mostly hidden from view. The theories we now hold about Earth's interior, the models of mantle convection, the picture of the core generating the magnetic field through dynamo action, the maps of seismic structure that reveal the heterogeneities throughout the mantle, are vastly better than what was known a century ago, built on far more data, tested against far more observations, refined through decades of careful work. And yet they remain, like the theories that preceded them, constructions built from indirect evidence, interpretations of signals rather than direct observations of the things themselves. There is no reason to think we have reached a final understanding, no reason to believe that future evidence will not require adjustments or even fundamental reconceptions of how we picture the deep interior. The history of geology suggests that major shifts in understanding occur when new types of data become available, when technologies develop that allow measurements previously impossible, when observations accumulate that do not quite fit existing models and demand new explanations. And there is no reason to think this process has stopped, no reason to believe that the current generation has arrived at final answers rather than at the best answers available given current methods and current data. This is not meant to undermine confidence in what is known, but rather to place that knowledge in context, to recognize that understanding the Earth is an ongoing process, that the planet is complex enough and remote enough in its interior regions that complete certainty may not be achievable, that some degree of interpretation and inference will always be necessary when studying a system from within it, when trying to map structures that lie beyond the reach of direct access. The Earth has been here for 4.5 billion years, forming and differentiating and convecting and evolving in ways that have left traces we can measure, but not complete records we can read without ambiguity. Humans have been studying it scientifically for a few hundred years at most, with sophisticated instruments and methods for perhaps a century, and with the theoretical framework of plate tectonics for only about 60 years. The ratio between these timescales is worth contemplating. The age of the planet against the duration of our study of it, the billions of years of geological history against the decades of modern understanding, the slow accumulation of rock and the patient movement of continents against the brief moment in which we have been here to notice and to wonder. Perhaps what the history of geological understanding reveals most clearly is that knowledge about the Earth is built slowly, through the accumulation of observations and the refinement of theories and the willingness to reconsider assumptions when new evidence demands it, and that at any given moment, what we know represents not a complete picture, but the clearest picture we can construct from the information available, subject to revision as better data arrives and as new methods of observation are developed. There is a particular kind of comfort that can come from accepting that some things remain unknown, not as a temporary condition waiting to be resolved, but as a more permanent feature of how we relate to the world. The interior of the Earth falls into this category, a domain we can study and model and learn about through indirect means, but one that will likely remain, in important ways, beyond the reach of complete understanding for as long as we are here to contemplate it. This is not a failure of science or a limitation to be overcome through better technology, though technology will certainly continue to improve and reveal new details. It is simply a consequence of scale and accessibility, of trying to understand a system from within it, of being small creatures living on the surface of something vastly larger and mostly hidden, creatures whose direct experience extends only to the thinnest imaginable shell and whose knowledge of everything below must be constructed from signals and samples and simulations rather than from witness. And perhaps there is something valuable in this condition, something worth preserving rather than lamenting, a relationship to knowledge that allows for uncertainty without requiring anxiety about what remains unresolved. The maps we have created of Earth's interior are remarkable achievements. Representations that show the general structure of the mantle, the location of the core, the approximate temperatures and pressures at different depths, the patterns of convection that drive plate tectonics and shape the surface world. They are the product of centuries of work, of countless observations synthesized into coherent pictures, of theories tested and refined until they match the available evidence. And they are useful, these maps. They allow predictions. They organize understanding in ways that reveal patterns and connections that would otherwise remain invisible. But they are not complete, not finished, not free from uncertainty or ambiguity. There are regions where the data is sparse, where different models disagree, where the resolution is too coarse to reveal features that might be important. There are processes that are understood in outline but not in detail, mechanisms that are known to occur but whose exact operation remains partly mysterious. There are questions about the deep mantle and the core that have been asked for decades and remain open, not because no one has tried to answer them, but because the answers require observations that are difficult or impossible to make with current methods. And perhaps this is fine. Perhaps the existence of these gaps, these places where knowledge fades into informed speculation, is not something that needs to be apologized for or anxiously worked to eliminate, but simply the natural state of studying something as large and as remote and as complex as a planet's interior. Consider what it would mean to have complete knowledge of the deep Earth, to know the exact composition of every layer, the precise temperature at every depth, the detailed structure of convection currents, the specific mechanism by which the geodynamo operates, the full history of how the interior has evolved over billions of years. Even if such knowledge were possible to obtain, even if we could somehow place instruments throughout the mantle and core and have them report back on conditions in real time, the amount of information would be overwhelming, more than could be processed or understood in any meaningful way, and much of it would be irrelevant to the questions we actually care about. What matters for most purposes is not complete knowledge, but adequate knowledge, understanding that is sufficient to explain the phenomena we observe, to make predictions that can be tested, to build models that capture the essential features of how the system works, even if they simplify or omit details that are either unknown or unimportant. The maps we have of Earth's interior serve this purpose well. They are approximations, yes, but approximations that work, that have proven their value through successful application, that continue to be refined as new data becomes available. They are not perfect, but they are good enough to be useful, which is perhaps all that knowledge needs to be. There is also something to be said for preserving mystery, for allowing some aspects of the world to remain partly unknown, not out of ignorance, but out of recognition that the unknown has its own value. The interior of the Earth, hidden beneath our feet, operating according to processes that unfold over millions of years in complete darkness and silence, represents one of the last truly remote regions of the natural world. Not remote in the sense of being physically distant, like the surface of Mars or the outer reaches of the solar system, but remote in the sense of being inaccessible, protected by conditions that make direct observation impossible. We live on top of it, walk across it daily, depend on it for the stable surface that supports us. And yet we cannot see it, cannot touch it except at its outermost edge, cannot experience it directly in any way that would allow us to say with certainty what it is like to be there, in the mantle or the core, surrounded by rock at temperatures and pressures we can barely imagine. This remoteness creates a kind of distance that is different from the distance of mere space, a separation that cannot be overcome simply by traveling there or building instruments that reach farther. And perhaps this distance is worth preserving, this sense of the planet as something that extends beyond the realm of what we can fully know, as something that holds depths we can study but not completely penetrate, as something that remains, in important ways, mysterious. The alternative, a world where everything is known, where every question has been answered, where no mystery remains, seems less interesting somehow, less rich, less worthy of continued attention. What drives scientific inquiry is partly the desire to answer questions, to solve problems, to build understanding where none existed before. But it is also driven by something else, by the recognition that the world is larger and more complex than our current understanding of it, that there are always new questions to ask, new observations to make, new ways of interpreting what we already know. The interior of the Earth provides exactly this kind of ongoing invitation to inquiry, a domain where much has been learned, but much remains uncertain, where the broad outlines are clear, but the details are still being worked out, where every answer raises new questions that require further investigation. This is not a frustration. It is an opportunity, a reason to keep looking, to keep refining methods, to keep thinking about what the evidence suggests and what it leaves open. And the fact that complete knowledge may never be attainable does not diminish the value of the partial knowledge we have, does not make the effort wasted or the understanding less meaningful. It simply places that understanding in context, acknowledges its limits while celebrating what has been achieved despite those limits. Perhaps the lesson, if there is one to draw from contemplating Earth's hidden interior, is that we do not need complete understanding to have meaningful knowledge, that uncertainty is not the opposite of knowledge, but rather its natural companion, that the limits of what we can observe and measure do not mark the end of what we can learn, but simply define the methods and approaches that are available to us. The planet has been here far longer than we have, will continue long after we are gone, and during the brief interval of our existence, we have managed to construct pictures of its interior that are remarkably detailed, considering how little of it we can actually access. That seems worth acknowledging, not with frustration at what remains unknown, but with something closer to satisfaction that we have learned as much as we have, and with recognition that the learning continues, slowly, patiently, in ways that match the timescales of the planet itself. The human lifespan is measured in decades, perhaps a century at most if fortune allows. This is long enough to witness seasons change, to see children grow into adults, to observe the slow accumulation of sediment in a riverbed, or the gradual erosion of a hillside. But it is nowhere near long enough to perceive the motion of continents, or the convection of the mantle, or the cooling of the core. The processes that define Earth's interior operate on timescales that are so far removed from human experience that they might as well be eternal, unchanging, permanent features of reality rather than dynamic phenomena unfolding according to physical laws. A plate moving 3 centimeters per year will travel 3 meters in a century, roughly the length of a small room, and 30 kilometers in 1,000,000 years, enough to close an ocean basin or open a new one. But within a single human life, the motion is imperceptible, detectable only through precise instruments that can measure tiny shifts in position over years or decades, never through direct observation of the ground moving beneath your feet. The mantle rock that rises from the core mantle boundary might take 100 million years to complete its journey to the surface and back again, cycling through temperatures and pressures that transform it repeatedly, carrying heat through thousands of kilometers of stone, in a flow so slow it defies any intuitive sense of what motion means. This disparity between human timescales and geological timescales creates a fundamental disconnect between our experience of the world and the way the world actually operates at depth. We live in a realm of days and years, of changes that occur quickly enough to notice, of causes and effects that are separated by intervals we can hold in memory and connect through observation. The Earth, meanwhile, operates primarily in a realm of millions and billions of years, of changes that accumulate so slowly they are invisible within any span of time a person might observe, of processes that link events separated by such vast intervals that no direct causal chain can be traced through human witness. We can understand these processes intellectually, can build models that describe them, can measure their effects and confirm that our theories match the evidence, but we cannot experience them directly, cannot watch them unfold, cannot develop the kind of intuitive familiarity that comes from repeated observation. The interior of the Earth exists in a different temporal regime than the surface world we inhabit, operating according to the same physics but at scales that place it beyond the reach of lived experience. Perhaps this is why the interior can feel abstract, even when we know it is real. Why it requires effort to remember that beneath the solid ground lies thousands of kilometers of hot rock, slowly churning, metal circulating through the core, heat flowing outward from the center in currents that have been moving for longer than life has existed on the surface. The evidence for all of this is solid. The seismic data, the magnetic field, the volcanic rocks that bring fragments of the mantle to the surface, the motion of plates that can be measured with GPS. But the phenomena themselves occur in darkness, at depths we cannot reach, over timescales we cannot directly observe, in ways that feel removed from the immediate tangible reality of soil and stone we encounter at ground level. It is not that the interior is less real than the surface. It is simply that its reality operates in a register that human perception is not well equipped to grasp, that requires translation through instruments and models and mathematical descriptions before it becomes comprehensible. And in that translation, something is inevitably lost, some sense of directness, some feeling of connection to the actual physical processes occurring below, leaving us with knowledge that is intellectually satisfying, but experientially distant. There is a kind of humility that emerges from contemplating this gap, from recognizing how small our observational window is compared to the full scope of what exists and what occurs. We stand on a planet that is mostly interior, mostly composed of regions we cannot see, and we have learned to interpret signals that travel through those regions, to build pictures from echoes, to infer structure from behavior. The knowledge we have constructed through these methods is genuine and valuable, but it is also necessarily incomplete, partial, limited by what can be measured from the surface and by how much can be reliably inferred from those measurements. There will always be details we do not know, processes we do not fully understand, questions we cannot answer with certainty because the information needed to answer them is inaccessible, or because the phenomena are too complex to be captured completely by any model we can construct. And perhaps the appropriate response to this situation is not frustration or anxiety, but something closer to acceptance. A recognition that the limits of our knowledge are set partly by the nature of what we are trying to understand, and partly by our position as observers confined to the surface, looking inward through layers of rock that filter and transform any signal we might use to learn what lies beneath. This does not mean we should stop asking questions or seeking better understanding. The scientific study of Earth's interior continues, driven by curiosity and by the practical importance of understanding how the planet works, and each new measurement and each refined model adds incrementally to what is known. But it does suggest that complete knowledge might not be a reasonable goal, that some degree of uncertainty might be intrinsic to the situation rather than a temporary condition waiting to be resolved, that the interior might remain partly mysterious not because we are failing to study it adequately, but because its nature makes certain kinds of certainty unattainable. The recognition of this limitation is not a defeat. It is simply a realistic assessment of what is possible given the constraints we work within. An acknowledgement that understanding can be meaningful and useful, even when it is not complete, that the maps we have drawn of the interior serve their purpose well, even though they are approximations rather than perfect representations. What remains then is a planet that holds depths we can study, but not fully know, layers that respond to our inquiries with signals we can interpret, but cannot definitively decode, structures that exist in regions we cannot enter, and that operate according to processes we can model but not directly witness. The Earth keeps its interior mostly to itself, revealing it piece by piece through the limited channels available to us. And what we have learned through these channels is remarkable considering the obstacles involved. But the learning is ongoing, incomplete, always subject to refinement as new data arrives. And the interior remains, in important ways, a frontier. Not a frontier in the sense of unexplored territory waiting to be mapped, but a frontier in the sense of a boundary between what can be known with confidence and what must remain, at least partly, a matter of informed interpretation. And there is something peaceful in that recognition, something that allows us to appreciate what has been learned without demanding certainty about everything, to hold knowledge lightly enough that it can be revised when necessary, to remain curious about what we do not yet understand without being troubled by the fact that some things might never be fully understood. The night has deepened while we have been thinking about these things, and the silence that surrounds us now feels different somehow, heavier perhaps, more aware of its own weight. The ground beneath remains as it has always been, solid, dependable, offering support without requiring acknowledgement. And yet knowing what lies below changes the quality of that solidity, adds layers of meaning to something as simple as standing still. Thousands of kilometers of rock extend downward from this spot, arranged in structures we have named and mapped and studied through the limited means available to us. And all of that immense architecture exists in permanent darkness, moving slowly through time according to processes that began long before anything lived on the surface and will continue long after. The crust, thin as paper when measured against the planet's radius. The mantle, vast and patient, convecting at speeds too slow to perceive. The core, liquid and solid both, generating the magnetic field that wraps around the Earth and extends into space. These are real things, actual physical structures, not abstractions or theories, but solid matter arranged in specific ways, responding to heat and pressure and gravity, participating in flows and transformations that shape everything, from the distribution of continents to the existence of the atmosphere. And yet they remain, for all practical purposes, invisible, known through inference, through signals that return from depth transformed, through models that organize our observations into coherent pictures, but cannot claim to be the territory they map. Perhaps the planet does not require being fully understood. It has existed for more than 4 billion years without concern for whether anything observed it or studied it or wondered about its structure, and it will continue regardless of how much we learn or fail to learn about its interior. The processes that operate at depth are indifferent to our curiosity, neither helped nor hindered by our attention, functioning according to physical laws that care nothing for observation or interpretation. The mantle convects whether or not we can image its currents. The core generates its magnetic field, whether or not we understand the dynamo mechanism completely. The boundaries between layers exist, whether or not we can measure their exact depths with precision. Our knowledge adds nothing to the planet itself, changes nothing about how it works, affects nothing about the slow, patient unfolding of geological processes across timescales that dwarf civilizations. What knowledge adds is something else, a different way of relating to the ground we stand on, a sense of connection to structures and processes that extend far beyond the visible world, an appreciation for the complexity that underlies apparent simplicity, a recognition that solid ground is not a simple thing at all, but rather the surface expression of a planet-sized system that has been operating for longer than we can properly imagine. And perhaps it is enough to know that the depths exist, that beneath the familiar surface lies this vast interior, that the planet extends downward into regions we can study but never fully illuminate, that mystery persists not as a temporary condition, but as an intrinsic feature of trying to understand something from within it. We have learned remarkable amounts through patient observation and careful inference, have built maps and models that reveal structures no one could have guessed at before the methods existed to detect them, have traced the motion of plates and the convection of the mantle, and the generation of the magnetic field with a precision that would have seemed impossible a century ago. And at the same time, vast uncertainties remain, questions that cannot be answered with available data, details that lie beyond the resolution of current methods, processes that are understood in outline but not in their full complexity. Both of these things can be true simultaneously. That much has been learned and that much remains unknown. And perhaps the appropriate response is neither pride in what has been achieved nor frustration at what remains beyond reach, but simply a kind of quiet acceptance, a recognition that this is what knowledge looks like when it concerns systems too large to hold in view, structures too remote to touch, processes too slow to witness unfolding. The Earth continues its work beneath us, patient and unhurried, following patterns established billions of years ago, slowly cooling, slowly cycling material between surface and depth, slowly transporting heat from core to crust in currents that flow through solid stone. We stand on its surface, brief and small, listening to the echoes that return from below and building pictures from those echoes, learning what we can through the limited channels available to observation. And when the observations end, when the instruments fall silent, when we turn away from the data and the models and the maps, what remains is simply the ground itself, solid and quiet, holding depths we cannot see, keeping its structure mostly hidden, offering no answers to questions we have not yet learned to ask, continuing as it has always continued, unmoved by our curiosity, indifferent to our understanding, present in ways that do not require acknowledgement or interpretation or any response at all, except perhaps the quiet recognition that it is here, beneath us, extending downward into regions we can imagine but never visit, into darkness that has existed since before there was light to contrast it against. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.